My name is Dr. Clint Barineau. I am a professor of geology at Columbus State University, and I'm standing here next to the Chattahoochee River in downtown Columbus. You can probably hear the river in the background. If you look upstream, you might be able to see the rapids, the last big set of rapids on the whitewater course. You can hear the sounds of the river around me. You might hear the traffic. You can hear some people on the zip line enjoying a nice afternoon on the river. We're going to ask ourselves a very important question as part of Earth Science Week, and that is, why is the city of Columbus here? And the answer happens to be the river. The river itself provided the raw, basic energy and materials that the city of Columbus needed to be economically successful. And the reason for that happens to deal with the geology. And so we are standing here on what we know on the Gulf and East Coast as a geological boundary referred to as the fall line. And so that's what we're going to be exploring in our lecture today on how the city of Columbus came to be. So you can hear the roar of the river behind me. We're standing right here where whitewater rafters put in on the Chattahoochee River. Take a short trip downstream over some extremely large rapids to the farthest point north on the Chattahoochee River, which is navigable from the coast. And this is why Columbus is here. Columbus was established in this region to take advantage of the fact that we have significant elevation drop as we come over a geological boundary known as the fall line. The fall line separates rocks of the coastal plain to the south from rocks of the ancient Appalachian Mountains to the north. And so the rocks we see in the river formed at the deep roots of a large mountain range that we know today as the Appalachians. As rivers flow across these deep-seated igneous and metamorphic rocks and then end up encountering the softer flat-lying sedimentary rocks to our south, they cut down into those sedimentary rocks and end up producing a significant elevation change. And so because of that elevation change, we can come in and put in dams along the river, take advantage of that to drive today modern hydroelectric power. But of course, back in the early 1800s, that was the energy source for the active mills that made Columbus famous and is the reason that the city is here today. So we're here on the river walk, just down from where all the rafters put in, and you can hear the river behind me, and the rocks that we see right here are part of a group, a geological unit that geologists refer to as the Phoenix City Gneiss. And the Phoenix City Gneiss was once buried under 20 or more kilometers of rock above our head. So once upon a time, these rocks are telling us we had a very large mountain range that stretched up over our head for a couple of tens of kilometers. These rocks were heated up to the point where they actually flowed like toothpaste. And if you look very carefully, you can see the white layers in the rock are very typical of rocks that form under those pressures and temperatures. So, When we look at these rocks, today we would refer to them as gneisses, or a closely related rock term, an amphibolite. An amphibolite is basically a metamorphosed basalt flow. So the rocks you see behind me were once basalts. Now you can go and see active basalts erupting out of volcanoes in places like Hawaii and Iceland. So once upon a time, before these rocks got caught in those collisions that produced the supercontinent of Pangaea, these rocks were actually active lava flows cooled off to make a black igneous rock or volcanic rock that we call basalt. So those basalts were trapped in the collisions that made that supercontinent, buried to great depth, and turned into what we know today as an amphibolite gneiss, or just a gneiss for short. So gneissic rocks are also actively mined to the north of downtown Columbus, and it's again one of the economic activities that go on in this area that are related to the underlying geology. Where I'm standing now is not far from Interstate 185, and the rocks that you see behind me are part of a geological unit that we refer to as the Tuscaloosa Formation. Now, the Tuscaloosa Formation is a layer of sands and gravels and clays that stretch through the state of Georgia all the way into eastern Alabama. In the Columbus area, the Tuscaloosa Formation consists of sands, and occasionally you'll see the weathered remains or the particles themselves of gravel particles that were being deposited in ancient streams. The white coloration that you see on this outcrop is the result of a clay mineral called kaolinite. To the northeast of here, towards Macon, there's enough kaolinite in those rocks to actually be mined. And so there are large kaolinite mines at this same geological boundary. In the case of Columbus, there wasn't enough kaolin here to be mined, at least not at this particular point in time, but as rivers flowed across the metamorphic and igneous rocks, which are very resistant to erosion and weathering, and they encountered these rocks can literally be broken apart with a spoon. And so those rivers began to erode deeply into this sedimentary unit called the Tuscaloosa Formation. The Tuscaloosa is the lowest sedimentary layer in the coastal plain. And so we're sitting right above the boundary between these coastal plain rocks and the igneous and metamorphic rocks below us. And so once those rivers encountered this kind of loosely cemented sands and gravels, they eroded and broke them down quite quickly. And so this led to the rivers having a very quick drop in elevation across this boundary, producing what we know as the fall line, the boundary between the navigable parts of the Chattahoochee River as we come up from the Gulf of Mexico, and the non-navigable parts as we go from Columbus up towards the city of Atlanta.